Okay folks, so in this video we're going to do a second attempt at showing the integrating factor method for solving linear ODEs. So first of all, notice that this ODE is linear in that I can write it in the form dy dt plus, then I'd have 3t over t squared plus 1 y is equal to 6t all over t squared plus 1. And this does indeed have the formula y prime plus a of t y equals b of t, which in the previous video we said was the form that we can write a linear equation in. So we're able to do so this is linear, so we can solve it using this integrating factor method. So let me just outline the steps for that. One, put in form y prime plus a of t y equals b of t, put it in that linear form. Then two, compute the integrating factor, where the integrating factor, it would be mu of t equals e to the integral of that linear coefficient in front of the y dt. The third step is to multiply this to both sides. Four is on the left side is we're going to recognize the form f g prime plus g f prime, and we're going to fold that up as the derivative of the product of f and g this way. So that's that technique of recognizing the product rule. Then lastly, we will integrate both sides. Both sides and solve. So let's go ahead and do that. So I've already done step one here. We put it into this linear form. The next step is to compute the integrating factor. The integrating factor would be mu of t equals e to the integral of 3t all over t squared plus 1 dt. So we're going to have to integrate this. And so you could do a u substitution if you wanted on this. This comes out to be e to the 3/2 times the natural log of the absolute value of t squared plus 1. And I would double check that. Folks, as a reminder, I'm not going to usually write this, but there is a plus c there, but then we always pick c equal to 0 whenever we do this. So now that we've got our integrating factor, we better clean it up a little bit. This is going to clean up to be t squared plus 1 all to the 3/2 power. And for this we need to assume, well actually we don't need to assume anything because the expression t squared plus 1 is always greater than 0. So let's continue. So there's our integrating factor that we're going to multiply to both sides of this equation. So I'd like to go ahead and do so. Here we go. So now I'm doing, so that was step 2. We found the integrating factor. Now we're going to multiply that to both sides, so I'll do so. This gives me t squared plus 1 to the 3/2 y prime plus 3t over t squared plus 1 times t squared plus 1 to the 3/2 y is equal to, and then let's see here, over here, when we multiply by that expression, we just get 6t times the square root of t squared plus 1, or if you like, to the 1/2 power. So the whole reason why we do this is because we recognize that it's of this form, and we can go ahead and simplify the left-hand side by saying that here we've got a product rule. Here's the first function times the derivative of the second plus the second function, plus the second function times the derivative of that first function. And so sure enough, this whole thing factors up very nicely as just, oops, that's too thick, as just d dt of the first, which was t squared plus 1 to the 3/2 times the second, which is always y. And then in the right-hand side, we just have what we have. So it's 6t square root of t squared plus 1. Okay. So we're running through the steps. We're now on step 5, where we can go ahead and integrate both sides. So integrating both sides is just going to give me on the left-hand side just the expression inside the derivative. And so I usually don't even write an integral symbol on that side. I just go ahead and say, well, when I take the antiderivative of this derivative expression, I just get that expression. And then on the right-hand side, we've got 6t square root of t squared plus 1 dt. So continuing to solve this for y, let's see here. On the right-hand side, I believe we get... So double check that. Let's see if we bring down the 3 halves. That gives us 3 times t squared plus 1 to the 1 half, and then we'd have a factor of 2t. So yes, that does give us what we want. And now we can go ahead and solve for y. And so we get that y of t at last is equal to, and we have 2 times the quantity t squared plus 1 to the 3 halves divided by t squared plus 1 to the 3 halves plus c over t squared plus 1 to the 3 halves, and we can clean that up, so let's go ahead and do so. We get y sub t is equal to just 2 plus c over t squared plus 1 to the 3 halves power, and there we've gone ahead and evaluated this using that integrating factor method. So folks, you're going to get a chance to practice this in just a second, but we're not quite done with this problem. Why? Because we were given an IVP, and so we need to actually solve for that unknown coefficient of c. So if we were to plug in 0 for t, that should output a 9. So if we went ahead and did that, we would end up with just that 9 needs to equal 2 plus c over 0 squared plus 1 all to the 3 halves. But that would tell us that 9 needs to equal 2 plus c, or c has to equal 7. And so then we'll just state the problem one more time, and I'm about out of room here, but we get that y of t is equal to 2 plus 7 all over t squared plus 1 to the 3 halves power, and there we've actually solved this IVP. So folks, here's a second stab at that integrating factor method. I've outlined the steps here. Oops, let's see if we can. I've outlined those steps here, and I'll let you practice through those on the next page. Go ahead and work number 8 using that integration factor. So go ahead and do that. This one is actually very similar to the one we just worked together. Fairly similar, except you've got a slightly different antiderivative to evaluate at the end. So go ahead and give that a shot, and let me know if you have any questions. This concludes your pre-work for Monday's class. Thank you.